So last time we talked about corner detector. So we will continue this discussion. So you can think of corner detector as like some kind of local feature extraction, right? So this time we will talk about I guess spend most of the time on SIFT or like kind of different variation of scale invariant feature detector. You basically like those. I guess is a review of what we did. Kind of the big picture here is like if you have like two kind of image that two objects there, you know that they are the same object. One way to kind of to match them is like first locate some of these key points here. So those key points are supposed to be distinct, and then like once you have the key points, we hope to be able to extract some descriptor. That descriptor hopefully will be kind of distinct as well. So you hope the descriptor is kind of like invariant to like scaling, rotation, and so on and so forth. So this is just an example for that. And so essentially, if you have a bunch of these descriptors, then if you're able to match that, then you're able to kind of identify this object is this object, so on. So last time we talked about Hertz corner detector, and I guess like some of you already mentioned, like some problem, as you can see, is that like if we only focus on corner, then it really depends on scale. So okay, actually last time like we say okay, basically the idea, maybe I'll just skip that anyway. So the idea of the corner, if you remember last time, is like the Hertz corner detector basically trying to find if you're locating a local patch there. Say if I try to see if this one is a corner, I'll just compare this neighborhood with a shifted neighborhood, like shift a little bit and see if it changes or not. So if it doesn't change in all the directions, then it's quite likely it's a corner. So as you can see, for a flat surface, if you move around, then it won't change, right? So and this is the basic idea there. And of course, like for edges here, if you move around, like if you move vertically here, there will be no changes. But if you move like horizontally, there will be changes. So so only when you have no changes in every direction, that basically is a corner. And last time, remember that like what eventually we want to speed up the computation, and so we will just compute this M matrix there. The M matrix is something like the gradient of different directions. If you remember, something like so M is something like I x squared, I think is I squared I x y x y y squared, something like that. So it's just gradient in horizontal and like kind of like diagonal, and also in vertical direction. And from this matrix, we derived last time that like you can compute some cornerless score. So the cornerless score is like basically you look at the eigenvalue of this matrix here. So if the eigenvalues, both eigenvalues, lambda 1 and lambda 2 are big, so more or less in this region, then it will be identified as a corner. So then the Hertz corner detector basically compute this. I guess it does not have a graph here for this function, but more or less it's like this value is big, then this will lie in this region here. So, and that's about it for corner. Yeah, and also like we mentioned that like afterward we need to do some like maximum suppression, so we don't want to have like too many response in a local region. So we just kind of like remove all the maximum response there, and Okay, come back to like what I originally said. So if I just use this harmless corner detector, as you can see, like from different scale, like maybe in the in the original scale here, like I may perceive this as a corner, but as I zoom in, then it no longer perceives as a corner. So we want to be able to fix that. So hopefully, like you want to have this feature extractor, this key point extractor, is kind of insensitive to scaling, and of course, like where you pick is insensitive to scaling. Hopefully, like afterward, the descriptor itself is also insensitive to scaling. So, but we'll focus on the how to extract the key point first, and afterward we'll talk about the descriptor itself. So, okay, actually, by the way, like, maybe I should pause a bit. Like, what's your suggestion if I want to build something? It's like environmental scaling. So probably I can do something similar to Harris corner detector, but I want to be able to kind of invariant to this scaling effect. Even though if I zoom in, I still able to kind of say, okay, I think this is still a feature, something like that, feature point, a key point that I want to. So what do you suggest if you? So any guess? Yeah. We can scale them. We can scale basically like a brute force way. Try different scale basically. So that's basically the idea that you get it. So we still like identify some cornerless score, like whatever, like feature score. Let's say this is we call this an F function there, but we look at this F function like, under different scaling. So we can change the scale, like given an image here, we just look at different scale of the image. How do we do different scale actually, by the way? Remember, what was the kind of like the typical way like you think like we can do? We roughly, quickly mentioned that like, I guess in one of the class. So we can form a pyramid, kind of like you just zoom in and then zoom in again, and so on. Like form a pyramid, and for different scales. So this is just an illustration. So what we are going to do is like we will just like consider a number of different scales there, and we will just compute this f function like for different scale for each of the point there. And then just see where's the local maximum there. So then we only consider the point is local maximum there. So if this maximum is like beyond some threshold, then for example, like this one way we can do it, then we'll say this is a key point, potential key point. And of course, a couple questions then, like what will be this f function? So of course, like one candidate is like we can use the Harris corner detector again. Like we can use that C function. Actually, indeed, like there's a paper using that, like the so-called Harris Laplace. What do they call that? Harris Laplace feature extractor, or like what? Let's see if it's just Harris Laplace. Like, so it's like feature detector, I guess. So basically, for that one, is like you can do in each scale, you compute the find. Oh, actually, I don't think it do every scale. It just in the original scale, it do Harris corner detector, but then it compute at different scale and look at where is the maximum there, and only take that maximum value at that scale to compute the actual descriptor. But I will more focus on the other method, a very famous method, the SIFT. So SIFT is like it's based on like a Laplacian function, but actually it's like approximate with a kind of actually more precisely a Laplacian of Gaussian. So you have a shape like that. So you have a Gaussian, and you compute the Laplacian is basically the second order derivative. So you have a shape like this thing. So you can imagine that this kind of you have like a high pass filter in all direction. Again, that like if something is flat, then you will have low response there. If, for example, if you have a dot here, and I mean outside is like either positive or negative. So these two different values here. If I have this kind of LG like exactly move to here, then I will have this peak here catch this dot here, right? So and give me a positive response. And so depend on different scaling. So for example, like I have a smaller scale like LG, then maybe it's not responsive to this guy, but we have a bigger LG, we respond to this guy, something like that. But it doesn't matter because we consider all the scale there. So and in practice, I actually SIFT does not use LG precisely. Actually, use a difference of Gaussian. So a difference of Gaussian is like let me, if I can have a figure to illustrate that. Actually, I don't. That's weird. I thought I have. So basically, you just have if you look at actually this have this one is more or less like it. So this blue curve is the Laplacian, and you have Gaussian in different scale. So and then when you have like Gaussian from different scale and you subtract to each other, this difference of Gaussian is more or less pretty much similar to a Laplacian. So so basically this is you see this is a Gaussian in scale with a scaling factor of k sigma, and then this is a Gaussian with a scaling factor of sigma, and you subtract them each other. So basically what I want to say is that I have something like you have the variance or like the standard deviation is k sigma, something like that, and then you have some other Gaussian that is like have a smaller variance like this, and when you subtract these two together, then you form something similar to or if I subtract this by this, then something like this way. So it's kind of like a Laplacian basically. So why he wants to do that is like it's mainly for computational efficiency, because like what he's thinking, okay, for each level I just compute the Gaussian anyway, I will need to compute it anyway, and then afterward I just subtract two levels, one level from each other, and then I don't need to compute Laplacian for each of the levels. And so anyway, it's quite similar to a Laplacian, and it works quite well. And in practice, like after he finds this like DOG like for each of the level there, it basically just find the local maximum as the potential candidate. So local maximum in all direction, basically like it's not just in the spatial, but also like in the scale direction. So as is the scaling, if like this is a local maximum like across everywhere, so I will consider this as a potential candidate. So any question? This is like the basic idea of SIFT.
So is this
Yeah.
like pixel by?
Yeah, it's
For each-
pixel by pixel, yeah.
Okay.
So it will compute, for example, you start with this image, you compute the Laplacian in the original level, you have like this way. And then, sorry, not Laplacian, it's supposing this is compute the Gaussian, you have a smooth image there. Then it's like the pyramid, you go down, kind of like continue to have a, actually not exactly like the pyramid, but then like in the next level, you increase the variance a little bit, and then you do another Gaussian, and then another Gaussian, another Gaussian. But then you subtract one level with each other, then you get this like something like similar to Laplacian. And then for each of these level, then you look at per pixel wise, across like both like horizontal vertical direction and also the scaling direction, and pick the local maximum, and pick all local maximum as potential candidates. And so let's see, and I mentioned like the other kind of method, like by the way, is like there's a Harris Laplacian. This basically based on the Harris corner detector. And for SIFT, of course, it's like super famous. Even though like there's a lot of like kind of alternative now. So, but it's still like, I guess it's the first one is really very successful in terms of like shift invariance. So, so it's got really well known. And let's see. Yeah, actually here is just talking about the same thing I just mentioned. Yeah, this is actually, yeah, I should go to this slide. This is a better illustration. So original image, you have like different level of Gaussian filters, right? You just, and then afterwards you subtract level by level to get the Laplacian approximation, basically the DOG. So this is basically the candidates that what we get here. Here, like the illustration here is for different size of the circle, it's like illustrate different scale level. It got the local maximum here. So again, like similar to like Harris corner detector, we want to do some filter, like kind of like remove some of these candidates here. So some outlier rejection that one way proposed in the paper is like given a local maximum, we want to really look for that. Of course, like this one, when you compute this is just a numerical maximum. Like this one is bigger than all the rest of the label, then we consider as a maximum, right? Then because we can approximate the partial derivative along x, y, and scaling direction, and also Hessian. So actually we can do a Taylor series expression for this point to the real maximum. Real, not I mean like it's still actually an approximation, right? But so the maximum, if you do a Taylor series expansion up to second order. Oh, by the way, like be careful. This one is what's the size of this thing? Do you know what's the size of this thing? Like there's del x squared. So so this the x here again I emphasize here like it's both x, y, and also the scaling direction. So it's like 3 dimensions. So this is a second order, like this is actually a Hessian matrix. So it's like a 3 by 3 actually. This is like actually the d partial d squared partial x squared is actually like partial d partial wait, yeah. Yeah, partial d partial x square partial d partial x partial y partial d. Something like that, and then partial d partial x partial y, something like that. You see that. So maybe I fill in the entire thing. Partial y square. This is partial d partial. I think I use sigma. Okay, sigma square, something like. So this is partial d square partial y partial sigma, something like. And of course the matrix is symmetric. So then if you think of this as like you have Taylor series expansion that your function is like some what's that called, d lot plus x lot. There's a partial derivative here, partial d partial x, and then let's say I just call it h here for simplicity. Hx actually x minus x lot, something like, right? Or just x. Okay, I assume that the point there is just the origin, so hx. So this is x plus x charm for x, right? Then maybe I put a 1/2 here. Did I put a 1/2 here? Yeah, I put a 1/2 here. So this, if you look at this like the maximum for this guy, you try to take the derivative, right? So if I have a Taylor series expansion for this guy, so let's say this now is dx here, and so we now then like so this now note that this is actually okay. All my x is like now is like kind of like a column vector here. So x is like actually like xy sigma, something like that, right? And then like if I need to take the maximum, then I take the partial derivative with respect to x here. Then this guy actually, this, if you take, of course this is constant, is gone. I take partial derivative of this term with respect to x. What do I get? Actually I better put a transpose here. So if I think of this as a column vector, actually d del x is actually something like partial d partial x partial d partial y partial d partial sigma, something like that. So therefore, like actually, I need a transpose here. Just make it it's a row vector model column vector. So now, if I take partial derivative of this guy with respect to x, so what do I get? Oh, by the way, this look complicated, but be careful. This is just a constant. It's because after you take the derivative here, you actually put in the values at that location. That is actually, this is considered constant. Only this x here are variables. So do you know like how to? Okay, let's say these two are vector. Do you know what's this? So this is like a function, scalar function of x, right? So what I'm writing is like essentially is like the gradient, or if I call this function f, is essentially something like the gradient of x, something like that. It's just a different notation. But so this thing here is like, first of all, like this guy is just summation of a I xi, right? So it's like it's just a dot product of a and x. So, and then if I take this kind of like partial derivative of this, or like the gradient of that, is something like partial x1, this term here, and then partial x2. Let's say x is here is like x1, x2, just for simplicity here. Some a. So therefore, this is just a1 x1 plus a2 x2. Let's say just 2D here. This is also, this is a1 x1 plus a2 x2. So if I take this derivative, then what? I will just get back a1 and a2, right? So therefore, like in general, when you have something like that, this is just give you back like a, actually. So it is similar to what you have in 1D, right? If I 1D, if I have ax, I take x, a is a constant, it's just equal to a. But if a is a vector, you also get back a, basically. You can verify yourself. Is for example, if you have like this term here, let's say, if I have something like x transpose hx, this thing is again a scalar, right? If you multiply that, it's just a scalar. And I can take the x again. So x is vector here. I can take the and what you will get is something like equal to 2hx. Actually, I should be careful. It's equal to h plus h transpose x, something like that. But you can just do the same thing as what I did here. So it's like a homework exercise, because like this thing here, you can write it as a x x I j h I j x j, right? So if you take this partial derivative, like with respect to x, you will give you back hij xj and actually hji xi, something like that. So that gives you these two things here. But you can try it out at home, basically. So therefore, like if I take partial derivative of this guy here with respect to x here, so actually this is a constant, I have nothing. This one just get back like partial d partial x, right? And this I will get like h 1/2 h plus h transpose x. But h is like a symmetric matrix. H is a Hermitian, is symmetric. So therefore it's just 2h. So I have this just equal to hx here. So, and the optimum happen when this is equal to 0, right? So I just like in 1D, I just want to see where is the slope is equal to 0. So therefore I will get x is equal to let's see, minus partial d partial x, right? And I multiply h inverse on both sides, so h inverse, something like that. So so that's what I meant. So this is the h here that I just mentioned. So I will have the maximum there. So I at this point is the maximum. Then I keep iterate that, substitute back and forth. So just to have iteratively try to do the Taylor series expansion, Taylor series approximation, and then like basically if it converges, then it's fine. But we still want to see if like that maximum is like sufficiently large. So for example, like you take a threshold, if like threshold approximate 0.03, if the threshold is not big enough, then we discard that. So so this outlier rejection. Any question here? So And because we basically using a when you use DOG, it's not like the cornerless function we considered last time. It actually does not distinguish like whether it's a corner or a edge. So in this case, we need to explicitly remove edges as well. So we do something similar to like hash corner detector. So because the hashing matrix is kind of similar to the M, actually it's the same as M, I think. So you also have the lambda 1, lambda 2. What we want is like lambda 1 and lambda 2 should be like have different size. So if like both of them big, then remember this is a corner, right? And if only one of them big, is just edges. So then again, like we can compute the trace because like the trace of the matrix is just the sum of the diagonal. It's also equal to the sum of the eigenvalues. And we can also compute the product of the eigenvalues is basically the determinant. So we can just from the trace and the determinant get the product and the sum and the product of the eigenvalues. And note that like if I consider this ratio here, so this ratio like what I get if I let's say R is equal to lambda 1 over lambda 2, then this ratio if I just compute that, it's just equal to R plus 1 over R plus 1 square over R. And this is a monotonic function of R. So therefore, like if I want to say like R, I reject everything like R is bigger than 10. I can just compare this guy larger than like 10 plus 1 square over 10, right? Something like that. So I don't remember exactly that what threshold they consider, but you can adjust that, like what kind of up to what level you want to kind of reject that as edges. And by the way, also like you see we computed this xy, dxx, and so on, and of course like all this can be implemented or approximated with just a kind of like filter like this, right? So my dxx is just simply doing like kind of second order, have like 1 minus 1 convolve with like 1 minus 1 again, so therefore I have 1 minus 2, 1. So and this one I can have like 1 or 1 convolve with 1 or minus 1 convolve with minus 1 or 1. So like vertical convolve with the horizontal, then I get this filter here. So so that's basically SIFT actually. Any questions? Of course, this is only the key point extractor part, like extracting the key point, but we didn't talk about the descriptor yet. So just mention like a couple other key point extractor, like this method called maximally stable extremal region. As the name suggests, what it does is just do a watershed segmentation. Basically, you keep increasing the level, kind of threshold level, so you have segmentation effect like this. And you want to see like which region will have like kind of stay stable for a large range of parameter. So if that happens, then that consider a potential candidate for feature. And so this is some example for MSER. And that's it actually. I didn't include like too many different kind of key point extractor. Of course, I will mention also Harris-Laplace. That's basically use the corner detector. So I guess I'll move on to talk about now the descriptor. So you have the key point, so you selected the key point. Now we need to compute the descriptor. So two main ideas. So one is that you can just use a template. Template will be like, okay, that point you will just basically extract that region that is like the template, and you use that region exactly to match somewhere else. Then of course like this have like lots of instability in terms of like I mean not robust against like rotation and also scaling, so it won't be a very good candidate in general. So most descriptor are based on histogram. So and for example, SIFT descriptor, like as we're going to talk about, is based on histogram. So the idea is again it's pretty simple. Is using a so-called like HOG, is this a histogram of oriented gradient. So you have say the image, then you can compute the gradient of the entire image, right? So you basically take a derivative and you look at just the direction of each of the pixel where it goes up. And then you can just group like several of them. Like for example, in this case, in particular for SIFT case, you just take 4 by 4 at a time of these gradients, and then compute the histogram for that gradient. And then like for SIFT, like basically it will do like 4 by 4 this patch here. So therefore like you have a histogram of gradient that you have like 16 so many histograms like this. So like 16 of this. So and for each of the histogram, because it depends on like how many directions you allow. So typically, for example, in SIFT, you allow 8 directions there. So then you have like 8 times 16 in total will be like 128 so many elements there. So what I mean is like for this each of the histogram, like you have 8 bins there, so therefore you have 8 values for each of the histogram, and you have like 16 histograms there, so therefore you have 128 so many values in total in terms of the descriptor. So this is the overall like basic idea. So there's some tiny refinement there. See. So first refinement is you want to do some scale invariance. So if you just like do the histogram directly, you don't have like scale invariance, right? So the idea is like I would just pick the for example, I compute like the histogram, I mean the oriented gradient over the entire this like patch, like 16 by 16 patch. I will pick the gradient, like the largest gradient, and just rotate to that direction basically. And then if I rotate to that direction, then I will, assuming that like, maybe I'm histogram. So, but anyway, yeah, I guess it. I can't forget later. Do I rotate after I compute the histogram or before the histogram? So according here is after the histogram. So like, so I yeah, this one I guess I'll probably double check. I won't just, but yeah, of course I think like you can also like do just like compute the oriented gradient and pick the largest one and then shift to that, like to rotate to that largest gradient there. the direction of largest gradient there, and then compute the oriented gradient again in that like rotated image. And then afterward, then you can have a scale invariant like feature descriptor. And another minor adjustment is like when you compute this histogram, typically you want to have a windows like something like this, kind of a Gaussian windows, just to have a light decay like near the boundary. So then when you move to like different area, it doesn't have this kind of rectangular boundary effect there. And there's some other refinement that I probably should mention is to avoid some of this specular highlight effect, that if you have some surface that is extremely bright, then that tends to affect your curve descriptor the value of your histogram there. What we can do is we can just clamp off those values, like when it's like larger than certain values there, for example larger than 0.2, we just like clamp it off, like just set it to 0.2, so to avoid some of this lighting like illumination saturation. And then we normalize. And so okay, that's basically I like to talk about SIFT. And there's some of this result here, but I guess it's PTO. I won't leave it here. I also like to mention that there's some kind of variation of SIFT, like for example, like there's first modification called surface. Again, a very famous a fast approximation of SIFT, and actually like often people now will also use surf as an alternative in contrast of SIFT. And actually, by the way, in OpenCV, there's like quite a few different descriptor you can like already implemented, and you can try it out. Actually, SIFT and surf there are a couple that I didn't mention here, but you can take it up. And also like maybe just as a side note, also want to mention like some other form of descriptor. Let's say there's a work by Malik in like 2001. It formed kind of like using a histogram idea, but consider a bean have a kind of a shape like this, and just counts the number of pawns in the beans there. So and there's also like other descriptor, like for example like based on self-similarity. So this kind of descriptor will be useful to kind of like match objects such as, for example, like this. I have a heart shape here, even though they have different texture, but they can match each other. So this is another example there. Oh, by the way, I want to also like say something about LBP. Like this is like again like pretty simple, but it's also like a very useful descriptor. The idea is like kind of quite different from the histogram idea. So you have an image, let's say an image patch here. I can like try to code this patch by just comparing this current pixel with the labeling pixel, like whether it's like the labeling pixel is bigger or smaller, and use that, and then we can code it as 1 or 0, something like that. And this is more You can imagine this can be more robust kind of like comparing with some other method, because you can have this intensity change a little bit, but it won't actually change this representation here. Right? And after you have this one MCO, you can just code it as one, because it's just a binary number. Then you can just code into a binary number, then we just get one number for that neighborhood there. So it's a very, very efficient representation. And we can kind of extend that. For example, like by the way, this is just some illustration that like for different shape you may have. If I have this point is bigger than all the rest here, then I will have spot there. If I have something flat and or like a bigger spot, maybe like I have this one and it's not bigger than like the rest, or like not have like similar values there, then I may have line n if like I have this point bigger than like just some of these points here, these 2 points here, so it's like a line n like going to this here. So I can also have an edge like this point is like bigger than just one side of the points there, or like a corner. So then it's a pretty concise like representation, and you can just from that number, then you can actually also identify whether there's a corner, edge, and so on and so forth. And we can extend this LBP idea to just not compare to the immediate neighbor, but also like the outer neighbors. So for example, I can look at the neighbors like two, not 1 pixel away, but 2 pixel away, and approximate at this location there, and even like, for example, 4 pixels away. And we can combine these representations together to form even kind of cascade them to form an even larger descriptor. And to make it rotational invariant, by the way, like, I guess everyone is almost fall asleep now. So maybe just any idea if I can make this thing like rotational invariant, kind of like just say. By the way, do you get like this idea here, like how this LBP is formed, the basic LBP? How can I make it this rotational invariant? Oh, I mean like, so I have a descriptor like this, right? So what I mean is like, if I have my pixel, something like that, is I got rotated. So let me give an example like this. Let's see if I can write. So rotation meaning that, like, for example, if this patch approximately rotate by 45 degrees, then maybe my value will be more or less like this way. So maybe my 1 move up to here, 1 move up to here, then my 2 move to here, then I have 7 here, 3, 8, 2, 3, 5, like this way. Then now if I try to compute the LBP, I have a representation. It's like, now it's what? This 0, 0, 1, 0, 1, 0, 0, 1. Now I count from here, then my value is 1 plus 8 plus 64. So it's equal to 64 plus 8 plus 1. So it's 73. So I have a representation of 73 after this rotating by 45 degrees approximately. How can I build a rotational invariant feature? Rotation invariant descriptor. So say like even I have the image kind of rotated, my descriptor is still kind of same as before. Let's say it's still like hopefully 146.
You could run it multiple times on different orientations of the image.
Maybe, but which one you decide as the finals? Should we cascade all of them together? Oh, no, not yet. Wait, I think like what he means is like, if I compute, yeah, actually, what do you mean by the another orientation? So
like if you rotate the image and then
yeah,
filter
rotate,
off again,
yeah. So then you close, but you don't. Do you need that? Do you need that? So when you say rotate, that essentially means that like. First time I start counting from this is the least significant bit. Then second time maybe I cut this one as least significant bit and do clockwise, right? I can do like rotate the filter. There's no filter here. Wait. What it's doing here is just simply comparing with the label. The label. I mean the label pixels compare with the center pixel. But Scott said, I think it's pretty close. Yeah. But you don't need to compare all of them, right? So I think like, yeah, you said like rotate the filter is essentially the same as saying, okay, I can take this one as least significant bit and then this one as least significant bit, this as least significant bit. Then each time if I have like different one as least significant bits, then I have 9 different values maybe. Then of course like these 9 different values, even after the rotation, I still have like same 9 different values. But in terms of matching, it will be more complicated because I still have shifted. Like I have the first set of 9 different values, these 9 different values, even though they belong to the same set, but they are at different location there. It's simpler than that. So one way is may not be the best way, more the most robust way. But one way is that we can just take the largest value as an anchor. For example, like every time we will take this one as the least significant bit or most significant bit, right? So then even after rotation, this one is still the least significant bit. So then each time is still starting from here. It's like 1 whatever, like so. Every time will be like in this case if I always go clockwise, then will be like 1 4 what's it 8 16 32. So then this will give me 37. So even like here, like I also get 37, right? Because this is again 1, this is 4, and this is like 32. Yeah. So that's I don't know whether it's a separate paper or something. Like if you're lucky at that time that know this, and then maybe you can simply write a very pretty nice paper and with a very simple idea. But so I guess that's about it. Review local descriptor. Yeah, actually, yeah, what we just mentioned, like most of these descriptors usually do not use color because it's hard to control color. So if you change the lighting, it can, yeah. So so typically we would change to grayscale and then like, well, this just a slide that but this is pretty old. I came across, and if you go to the slide, I find another paper compare just like the several of the descriptors that implemented in OpenCV. So if you're interested, maybe that other paper is more interesting because in practice, if you don't actually do research on descriptor, you just as a practitioner, maybe that other paper is more useful because like
Where can we find that?
you can just click this one.
On your slide?
Yeah. So and I think like OpenCV implement a serve and SIFT, and also they have something called I don't know how to pronounce that. If I'm Japanese, I call it kaze, but it's like kas or like I don't know how to. But there's also I think it's by some Australian group. So and they have also a kase or a kaze or a akas. So it's like accelerated version, and there's a brick. I don't know. But anyway, like if you look at the documentation in OpenCV, I will just show you afterward, like as a demo. So I guess what?
It's a link to a file on your computer.
Oh really? Okay, okay, yeah. I didn't. Okay, let me just. I'll go back and update the link. Okay, I guess I'll stop here for the slides, but we'll just take a quick illustration of like the. See if I have a camera here. Let's see. What's that? Maybe I start again. Oh, I didn't save. Okay, I guess I can copy here. And if you remember, this one is just doing a. Okay, let's see. I shouldn't break it so quickly. I didn't save. Let's see. SIFT detector, key points, descriptor frame. I don't know whether I can just frame. Let's see. Show image 2. Let's see if it works. Oops. Wow. Okay, it is working. So let's So of course I didn't show the descriptor. This is just showing finding the key point. So what's that? Let me see. Like I forgot. This one I think is SIFT. So yeah, SIFT. Maybe I should just call it DSC. Then I can change different of them. So that's I tried several of them. Like they have like what? Yeah, that's I can change it to serve, for example. But even SIFT is quite quick actually now. Of course, I'm after so many years. So I think the paper is what 2004 or something. I forgot. So definitely, like I remember one of you guys talk about project, right? I think like using this kind of descriptors probably is fast enough if you look for an object that you know exactly, basically you know exactly what is that object. For example, like I guess some of you guys last time discussed with me with like what looking for package or something. So if you have an exact logo on the package, then maybe this kind of algorithm will work well. And computational wise, it's not very expensive. So you find the, and once you find the, I think it also even already find. Let's see. Yeah, I think already computed descriptors also, like not just computer key points, already computed descriptor. There's several, like as I mentioned, there's bricks, like Kase, and this several, and you can just try it out. Like so maybe I try one more. I remember this one is actually pretty slow. Yeah, this one is pretty slow. I don't know. But the accelerated version is okay. This acceleration. Yeah, this is quite okay. So, but anyway, like I think like yeah, you can use this like for project. Like it's easy to make it work like in OpenCV. And of course, for commercial product, like you may need to pay for the license because many of these are non-free. So it's in the non-free package. So when you install OpenCV, oh yeah, by the way, yeah, if you remember, when you install OpenCV, we say like PIP install, right? Let's see. So I think it's like Python OpenCV or OpenCV Python. I don't remember. Yeah, OpenCV Python. But because this is non-free, I think it's in the contribute. Yeah, you need to install this package as well. Oh, I'm not sure you can see it. I'm sorry. Let's see. Yeah. So you're supposed to install this one for like if you want to use, for example, SIFT and I guess many other this kind of descriptor and key point extractor, they are not in the original package because it's not a OpenCV. The library is just include all the license-free like algorithms there. So okay, I guess I will stop here. So I will see you guys on Thursday.